In this video, we are going to talk about the concept of resonance and how it relates to Lewis structures. Resonance is a stabilizing feature of a molecule, which means it brings the energy of the molecule down to a lower state. It is more stable this way. And resonance occurs when you can draw two or more valid Lewis structures for the same molecular ion, where only the electron placement is different. If you rearrange the atoms, that is not a resonance structure, that is an isomer. Resonance structures only have differing placement of electrons. So let's do, for example, sulfate ion. Now, if we draw the Lewis structure for the sulfate ion, there are a couple different ones we can draw. We can draw one where sulfur is bonded to 4 oxygens singly, and then we have all the remaining extra valence electrons on the outside, and there is a 2- charge to that. There is another way that we can draw this where the electron placement has changed. Imagine that if we want to expand the octet, one way that we can do that is if that pair of electrons becomes a bond, as does that pair. Now, what we get from that is a sulfur with 2 double bonded oxygens and 2 singly bonded oxygens. Now, why would we do that? Why would that happen? The reason is the sulfur is actually more stable when it's doubly bonded twice to the oxygens. These two structures are indeed resonance structures because the only thing that I've changed is the placement of the electrons. Now, sulfate actually has a total of 7 resonance contributing structures. Now, these 7 resonance contributing structures only differ in the placement of the electrons. And what you would see is these electrons would change positions, and you could draw a total of 7 different ones. Now let's take a look at carbonate. Carbonate has 3 resonance contributing structures. With 1 double bond. And don't forget, we got to put the charge on the outside. Now, what if these electrons decide to become double bonded? That's going to push those electrons up to that other oxygen, and that gives us our second resonance contributing structure, where we have an oxygen that's singly bonded, carbon double bonded to an oxygen, and then another single bonded oxygen. And don't forget the 2-. And the same thing could happen to the third, where those electrons decide to go there, and those electrons hop back up to there, and that gives us our third resonance contributing structure, where we have carbon double bonded to oxygen, singly bonded, and singly bonded. And don't forget the 2-. Now, the key thing here is that no one structure adequately describes the true nature of the molecule. Much like yellow and blue make green, the different resonance contributing structures add up to what reality really is. When we took a look at the carbonate ion, when we measure the bond length between the carbon and the oxygen, it's not like it's a single bond length or a double bond length, but it's actually in between the two. It's like a bond and a half, which helps support the idea that the resonance contributing structures are constantly going through, and each one contributes to the overall structure of the real molecule. Now, resonance is going to stabilize the molecule and make it harder to react, certainly, because the reactions occur at the electrons. And if the electrons can move around, they're harder to react at. And the best case for this is the case of benzene. Benzene is C6H6. Now, organic chemists tend to draw carbon and hydrogen compounds with just lines. So benzene actually has a structure that looks like this. Now, each vertex is a carbon atom, and we assume that we have enough hydrogen atoms to go around and fill up the rest of the valencies. And there are 3 double bonds, but that's only one resonance structure. We can have these electrons hop there, these go to that one, and these go in between there, and what we get is the second resonance contributing structure for benzene. And when we do that, this is what we have. Now, benzene is notoriously hard to react. It was actually a big problem when they were trying to decide what the structure of benzene was. They couldn't understand. They knew that it had unsaturation, which means it didn't have all the hydrogens it could possibly have to fill up the valencies. But it also didn't react like things that were unsaturated. For example, if you put bromine into an unsaturated compound, bromine is a brown liquid. That brown liquid reacts with the unsaturated, or with the double bonds that would be there. It would react with the double bond and go colorless. But when you put bromine in benzene, it just sits there. The reason is those bonds are actually smeared out across the whole molecule. So we oftentimes see benzene written like this, with a circle in the center, showing that we've got a resonating set of double bonds, and the electrons are all smeared out throughout the entire surface. And that is why resonance can help stabilize, and it makes resonance stabilized molecules sometimes harder to react. Now, if you want to read more about resonance and how it goes into the reactivity of chemistry, you can follow the link here, the Wikipedia link to chemistry resonance. It is a little bit more in-depth than we're going to cover in this class, but it is a good read if you want to learn more about resonance, and I hope you enjoyed this video.